So hello guys, once again I welcome here all of you in this marathon session of highway engineering where we discussed yesterday in our previous video of that pavement design. Last last night, yesterday's video we discussed the CBR method, equivalent C value and all of this stuff. Today we're gonna discuss triaxial test method, Mcleod method, Burmester method, and displacement equation by Burmester method and all of these things. Okay, so yeah, let's go to start with from triaxial test method. Yeah, so triaxial test method. Basically, we have a formula for in triaxial test method for thickness, that is T is equal to under root 3pxy 3pxy upon 2 pi es delta 2 pi es delta delta to the whole square minus a square. Okay, where T is the pavement thickness, where T is pavement thickness, pavement thickness in centimeter, and P is wheel load in kg, obviously. Oh, wheel load in kg. Okay, and obviously A is radius, and our delta is design deflection, design deflection, which is something equal to 0.25 centimeter. Okay, approx equal to that. Okay, and our x is equal to, x is traffic coefficient, this x is traffic coefficient, and our y is saturation coefficient, saturation coefficient. So yeah, this is all about in triaxial test method for thickness. Now let's move to our next thing in triaxial test method, that is for two layer system, thickness for two layer system, for two layer system. What if you have for two layer system? Okay, so we have formula that TP is equal whole bracket under root 3pxy upon 2 pi es delta 2 pi es delta to the whole square minus a square bracket close into es by ep power 1 by 3 ep power 1 by 3. So this is formula for two layer system, and if in numericals there's two thickness and you have to find two elastic values, then we have another formula that T1 by T2 is equal to E2 by E1, E2 by E1. Basically, this is a relation between T and E. Sorry, E2 by E1 to the power 1 by 3 by 3. Okay, so do remember these formulas, these two, and also these one, this. Okay, so this is all about triaxial test method. Let's move to Mcleod method. Find thickness. Mcleod method. Mcleod method. Okay, in this we have T is equal to small k log P by S, P by S to the base 10. Okay, where T is obviously required thickness of gravel base in centimeter, and our P is gross wheel load. Gross wheel load 8 kg. Our K is base course constant. Base course constant, and our S is total subgrade support in kg. It is in kg. So one more thing about S, that S calculated basically S our total subgrade support is calculated for 30 centimeter dia, 0.5 centimeter deflection at 10 repetition. TITION. Okay, so yeah, this is all about Mcleod method. Let's move to another method, that Burmester method. What it is? Burmester method. Okay, so if we're going to discuss Burmester method, let's draw a diagram for the sake of simplicity, that something like this. Here soil subgrade, soil subgrade, subbase course, and it is, here it is, base course. Let's denote for this. We have ES, ESB, E, B. In Burmester method, it is in between this is have relation something like this: ES greater than ESB greater than ES. Okay, but Bosnick's analysis is a special case of Burmester method, where EB is equal to ES is equal to ESB. Okay, that Bosnick's analysis Bosnick's analysis is a special case of Burmester method, and in this we have ES is equal to EB is equal to ESB. Okay, so this is all about ES, EB, ESB and Burmester method, and we also see that Bosnick's analysis is a special case of Burmester. Let's move on to next thing, which is a displacement equation given by Burmester. Displacement equation given by Burmester. Okay, so let's first see for flexible plate and then we go to for rigid plate. Okay, first see displacement for flexible plate. Okay, in this basically be done test over surface. Okay, deflection delta in this deflection delta is equal to 1.5 pa by es into f2. Okay, where delta is obviously our design deflection. Our p is contact pressure at road surface due to wheel load. Contact pressure at road surface due to wheel load. Okay, and a is radius of contact area. Okay, and our f2 is deflection factor, and our basically our f2 our f2 is deflection factor based on es by ep and h by a. What is h? Basically h is thickness of reinforcing layer. H is thickness of reinforcing layer. Okay, so this is all about for flexible plate. Let's move on to another thing, which is for rigid plate. Put that it right here. That is for rigid plate. Basically in this test we've done test over soil subgrade. Test over soil subgrade. And this will done test over soil subgrade. Okay, and for this we have a formula like delta is equal to 1.18 pa by es into f2. Okay, and uh in this for single layer, like in Bosnick's analysis, h is equal to 0 and es by ep is equal to and many more things, so that for single layer like in Bosnick's analysis, that h is equal to 0, es by ep is equal to 1, f2 is equal to 1, Poisson's ratio is equal to 0.5. It is Poisson's ratio, and plate dia is about 30 centimeter, and delta design deflection is something from 0.5 centimeter or 0.25 centimeter. So yeah, so this is all about displacement equation given by Burmester. Let's move on to another thing, that design of rigid pavement. Another topic, design of rigid pavement. Okay, and first here, modulus of subgrade reaction. You know, we discussed it earlier in our highway materials video. The same thing, modulus of subgrade reaction, which is k is equal to p by delta, where delta is deflection, which is something about 0.125 centimeter. And yeah, we already discussed it. Let's see it once again, that this graph here, it is something like this. Yeah, and there this is pressure, it is delta in centimeter, this is slope. Okay, so this is it, and you already know that p is our pressure. P is pressure which is sustained by rigid plate of the standard diameter, which is 75 centimeter. Okay, P is pressure sustained by rigid plate of standard 75 centimeter 75 centimeter dia at a deflection of 0.125 centimeter. Okay, it is 0.125 centimeter. Here it is pressure. Okay, so yeah, this is all about modulus of subgrade reaction. Let's move on to another thing, which is relative stiffness of slab to subgrade. Okay, what it is, that relative stiffness relative stiffness of slab to subgrade. So yeah, so for this we have a formula. It is that L is equal to EH cube upon 12K into 1 minus mu square. Okay, to the power 1 by 4, where basically we have value is equal to 3 into 10 to the power 5 in kg per centimeter square. Kg per centimeter square. Okay, and we have a value for mu is equal to 0.15, and yeah, and obviously k is our modulus of subgrade. Modulus of subgrade. Okay, so yeah, this is all about relative stiffness slab to subgrade formula. Let's move on to one interesting thing, that positions of critical loads, that critical load positions. Critical load is not so important, but let's say it is quite interesting. Okay, critical load positions. let's show here. Okay, here, here, and yeah, here. Yeah, so here it is interior load. It is corner load, corner loading. Okay, and it is edge loading, edge loading. Okay, so this is diagram and for critical load positions. Let's move on to another thing, which is equivalent radius of resting section. What it is that equivalent radius of resting section. Yeah, so basically for this we have a formula that b is equal to under root 1.6 a square plus h square. Yeah, minus 0.675 h, minus 0.675 h. This is when if a is less than 1.72 h, and this b is equal to a when if a is greater or is equal to 1.72 h. If a is greater or is equal to 1.72 h. Okay, where a is radius and h is slab thickness in centimeter. A is air radius and h is slab thickness in centimeter. Okay, so yeah, this is all about equivalent radius of resting section. Let's move to another important thing, that V load stresses that V load stress by Westergaard's stress equation. Stress by in V load stress. Give me a second. In V load stress, first thing is Westergaard's stress equation. Westergaard's stress equation. Okay, so for this, so we have a three formula for inner, for edge, and for corner. That for inner, SI is equal to 0.316 P upon H square 4 log L by B to the base 10 plus 1.069. And for edge, it is 0.572 P upon H square 4 log L by B to the base 10 plus 0.359 plus 0.359. Okay, and for corner, it is 3p by h square, 3p by h square 1 minus a root 2 by L, a root 2 by L to the power 0.8. So yeah, this is given by Westergaard's stress equation, where SI is stress at interior, where SI is SI S. Wait a second. SI SESC is stress at interior, edge, and at corner. Oh, okay. So yeah, and H is our slab thickness, P is wheel load, A is radius, and L is, which is discussed before that. Yeah, our L is here. No, not this. This one is our L is relative stiffness in centimeter. Our L is relative stiffness in centimeter. Okay, and our A is radius of wheel load distribution. A is radius of wheel load. Basically, it is in centimeter, and our B is radius of resting section. Radius of resting section. Basically, is radius of wheel load distance. Okay, resting section. It is also in centimeter, and our H is slab thickness and P is wheel load, which is in kg, so no need to write this. Okay, basically look, so this is all about Westergaard stress equation, and we need to do this, remember this formula, but now we have a modified part of this equation. So this formula, this one, this formula were modified by Westergaard and by uh, Teller and Sutherland. Okay, so now we're gonna discuss the modified version of these equations by Westergaard, by Teller and Sutherland. So the our formulas were modified by Westergaard and by Teller. Westergaard were later modified by Westergaard and Teller and Sutherland. And Sutherland. Okay, so let's see these modified formulas. Come on, man, go up. Yeah. So in modified stress in interior, so it is equal to 0.275 1 plus mu p by h square, p by h square log eh cube by log eh cube by kb to the power 4 to the base 10 minus 54.54 L by C1 into C2. L by C1 into C2. So this is equation for stress at interior, that is 2.75. This 2.75 into 1 plus mu into p by h square in, and then into in the whole bracket log ch cube upon log eh cube upon, this is e log eh cube upon kb k b to the p to the power of 4, this in this closed in the bracket to the base 10 minus 54.54 into L by C1 into C2. So this is for stress at interior. Let's Let's see. The stress at edge, it is something like 0.529 into 1 plus 0.54 mu and 54 mu into p by h square, p by h square in bracket log eh cube by kb power 4 log eh cube by kb power 4 to the base 10. Shit, man. To the base 10 minus log b by 1 minus mu square, b by 1 minus mu square to the base 10 minus 1.0792. Okay, so this formula for stress at edge, what it is, that 0.529 into 1 plus 0.54 mu and into p by h square and in the close bracket into log eh cube by kb power 4 to the base 10 minus log b by 1 minus mu square to the base 10 minus 1.0792. Okay, let's see for the corner. Stress at corner, it is equal to 3p by h square, 3p by h square into 1 minus 12 into 1 minus mu to the whole square into k upon eh cube into a root 2 power 1.2. Okay, so yeah, so this is the modified formula by Taylor, Sutherland and Westergaard. Here two new things were introduced, that c1 and c2, this c1 and c2, basically these are the correction factors to allow for a redistribution of subgrade reaction. Okay, so basically these are c1 and c2 are correction factors to allow for a redistribution of subgrade reaction, to allow for a redistribution distribution of subgrade reaction. Okay, so yeah, this is set in these formulas, guys. Do remember these formulas. Okay, I know this is quite hectic to remember this, but yeah, you need to do this because it will help you a lot in when you go to solve your numericals. This will help you a lot. Okay, so do remember these formulas. It is quite hectic, but if you revise over and over, then you'll remember that. Okay, so do remember these things. Let's move on to next thing, that again in the same thing, Pickett presented their two formulas, that let's see. Basically Pickett presented for corners only there are two formulas. Pickett presents two formulas. Yeah, so for Pickett presented basically for protected and unprotected corners. So for protected corners, protected corners, protected corners, we have SC is equal to stress at corners. SC is equal to 3.36 P by H square, 3.36 P by H square into 1 minus under root A by L, 1 minus under root A by L to the 0.925 plus 0.22 A by L, 0.925 plus 0.22 A by L. Okay, this is for protected corner. Let's see for unprotected corners. So for unprotected corners, we have stress at corners is equal to 4.2 P by H square, 4.2 P by H square into 1 minus the same thing under root A by L divided by 0.925 plus 0.22 A by L, the same thing, 0.925 plus 0.22 A by L, 22 into A by L. Okay, so yeah, this is Pickett's formula for protected and unprotected corner. Basically, there is a basic difference in protected corners and unprotected corners. That protected corners are one which transfer at least 20% of their load from one slab corner to the other, and unprotected corner is one which does not fulfill these criteria. Okay, so uh, let's write this, that protected corners are one which protected corners are one which transfer at least 20% of their which I'm sorry which transfers at least 20% of their 20% of the load from one slab corner to another, 20% of the load from one corner to the another, from one slab corner to the other to the other while unprotected corner is the one unprotect protected corner unprotected corner is one which does not fulfill these criteria. Okay, unprotected corner is one which does not fulfill these criteria, which does not fulfill these criteria, fulfill fulfill the above criteria. Okay, so yeah, this is protected and unprotected corners basic difference. Presented Pickett presented two formula about the protected corners, stress at protected corner and stress at unprotected corners. And for stress at interior, stress at edge, stress at corner, IRC also recommends their three formulas. So we have to look into that. So IRC recommends that stress at interior is equal to 0.316 P by H square into 4 log L by B to the base 10. 4 log L by B to the base 10 plus 1.069. 1.069. This is for stress at interior. Let's move to stress at edge. It is equal to 0.529 P by H square into 4 log L by B to the base 10 plus log B to the base 10 minus 0.4048. Okay, into close the bracket and into 1 plus 0.54 mu into 1 plus 0.54 mu. Okay, this is for it edge, and for corners IRC recommends 3p by h square. S is equal to 3p by h square into 1 minus a root 2 by L. A root 2 by L to the power 1.2. So basically these three formulas, this one, and this one, for interior, for edge, and for corner, IRC recommends. So do remember this formula because it is recommended by IRC. Stress at interior, stress at edge, and stress at corner. So okay, let's move on to another thing, which is temperature stresses. Another important thing is temperature stresses. Temperature stresses. Yeah, we have a formula for this. That here STI, that for interior STI, it is equal to E alpha T by 2 into Cx plus mu Cy upon 1 minus mu square. This is for STI, and for edge it is maximum of Cx E alpha T, Cx E alpha T by 2, or Cy E alpha T by 2, whichever is maximum. If value of this is maximum, take this. If this one is maximum, take this. Okay. And for corners, STC is equal to E alpha T upon 1 minus 3 into 1 minus mu, E alpha T upon 1 3 into 1 minus mu, 3 into 1 minus mu into under root A by L. Okay, so this is all about temperature stresses. Basically these are called warping stresses. Warping stress. Okay, here we have E is equal to 3 into 10 to power 5 kg per centimeter square. Okay, and alpha is equal to 1 into 10 to power minus 7. Yeah, alpha is equal to 1 into 10 to power minus 7, and A is our obviously our radius of contact area, a radius of contact area, and our Cx is divided into Cx by L by L, and Cy is equal to A by L. It's not C, so give me a second. It's called X by L, Cy is equal to L by L. Okay, and for mu is radius of relative stiffness, obviously. Our mu is equal to 0.15, and our L is radius of relative stiffness. Okay, so yeah, this is all about warping stresses at temperature stress. Let's move on to the next stress, which is frictional stresses. Wait a second, give me some time to set these pages. Yeah, so now our next is frictional stress. Frictional stress. So we have formula for this, that SF is equal to FWL upon 2 into 10 to the power 4. 10 to the power 4. Okay, where W is unit weight of concrete. Unit weight of concrete, which is something about 2400 kg per centimeter, which is something about 24 kg per meter square, which is about 2400 kg per meter square. And F is coefficient of subgrade. F is coefficient of subgrade, and it have maximum value of 1.5. Okay, and L is length of slab in meters. L is length of slab in meters. So yeah, do you remember these formulas, these frictional stress and warping stress, this one? Okay, let's move to another important thing, that critical cases of stress combination. And in this we discuss design of joint, expansion joint, contraction joint, and all of these stuffs, tie bar, and yeah, all these things. So, and Dowel bar. So let's move on to that. That is critical cases of stress combination. Critical cases of stress combination. In this we'll discuss first that design of a joint. First we'll see that expansion joint. In expansion joint, in this basically it should not have gap more than 2.5% in any case. uh, should not do not have gap more than 2.5 centimeter in any case. Gap more than 2.5 centimeter in any case. Okay, and basically IRC also recommends that for that gap for expansion joint, that IRC recommend that maximum spacing between expansion joints should not exceed 140 meter. Okay, so IRC recommends that maximum spacing between expansion joints should not exceed 140 meter. Should not exceeds 140 meter. Okay, so yeah, this is the restrictions, or you say the rule in expansion joints given by our IRC, and this is okay. So yeah, let's discuss one more thing in expansion joint, that delta by 2, one formula we have in this LL party. The delta is width of expansion joint, width of expansion joint. Okay, and T is obviously temperature. T is temperature, and L is length, and our alpha is thermal coefficient. is thermal coefficient. Okay, so yeah, this is all about the expansion joint. Let's move on to the another thing, that is contraction joint. Okay, so in this we have a formula that L is equal to 2 into 10 to the power 4 SF, which is frictional stress, into upon FW. Frictional, here it is, SF is tensile strength. It is of something about 0.8 kg per centimeter square. Okay, W is unit weight, as you already know. Unit weight, which is about 2400 kg per centimeter cube. 2400 kg per centimeter cube. Okay, and basically this is in cube actually. Maybe it is in centimeter also. Okay, you'll see it, this one. Okay, at yeah, here W is unit weight, which is equal to about 2400 kg per centimeter cube, and F is our coefficient of subgrade. Yeah, F is our coefficient of subgrade, which have a value about 1.5. Okay, so yeah, this is the thing in contraction joint. Let's move on to another thing, that frictional force. And for this we have a formula for that. So a frictional force, basically frictional force is equal to force in bar. Or so from these relations we'll get one formula, that L is equal to 2AST my ST upon FWBH. Okay, where sigma stays allowable tensile stress in steel. The sigma stays allowable tensile stress in steel. Okay, so this is it. uh, let's move on to next thing, with that is tie bar. Tie bar. So in tie bar, let's discuss design of a tie bar. Design of tie bar. So in design, first step is diameter of tie bar and spacing of them, of that spacing of tie bar. It is, and for this we have a formula of area, that AST is equal to FW into BH upon sigma ST. Okay, where B is depth, where B is width and H is depth. This one B is width and H is depth. Okay, and obviously W is unit weight and sigma ST is allowable tensile stress, which is about 1750. W is unit weight and sigma ST is allowable tensile stress, which is about 1750 kg per centimeter square. Give me a second. 1750 kg per centimeter square. Okay, so this is about the diameter and spacing of tie bar. Let's move on to the length of tie bar, which is that length of tie bar, that LT, noted as LT, it is equal to 2 LD, where LD is equal to phi sigma st upon 4 tau BD. So LT is equal to 2 into sigma into phi into sigma st upon 4 tau BD. Okay, basically phi is diameter, and tau BD is allowable bond stress. Tau BD is allowable bond stress. Okay, it is about something 17.5 kg per centimeter for plain bar and 24.6 kg per centimeter square for deformed bar. So it is about 70.5 kg per centimeter square for plain bar and about 24.6 kg per centimeter square for deformed one, deformed bar. Okay, so yeah, this is about length of tie bar. Let's move on to another thing, which is dowel bar. Dowel bar. Yeah. So what it is? Dowel bar. Let's say load transfer capacity of dowel bar. What? Load transfer capacity of dowel bar. Capacity of dowel bar. Okay. So first shear in the bar. We have a for shear in the bar. Shit, man. For shear in the bar, we have formula that PS is equal to 0.785 d square into Fs, 0.785 d square into Fs, where Fs is permissible shearing stress. Fs is permissible shearing stress. Okay, and for bending in the bar, we have formula for bending in the bar. We have formula PF is equal to 2d cube F upon LD plus 8.8 D plus 8.8 delta, where delta is joint width. Okay, and for bearing in bar, we have a formula for bearing in bar. We have formula PB is equal to FCLD square into D. FCLD square into D upon 12.5 LD plus 1.5 delta upon 12.5 LD plus 1.5 delta. Okay, so yeah, this is about dowel bar. Do remember formula about with these conditions. Okay, so yeah, this is it in Dowel Bar. We have also in the design steps of Dowel Bar, which is some theoretical portion, so you'll refer your book or any material for that. So but from here everything if about pavement design is completed. So yeah, this is it in pavement design. We'll very soon we'll discuss the previous year questions of pavement design. Okay, so yeah, till then do lot of questions about the gate examinations. And yeah, till then take care. Thank you so much for watching this video. Thank you.